Hello everyone. Now let's continue our learning journey. Okay, so on this journey, our objective is to calculate the potential due to a uniform solid sphere. Okay, and okay, so this is a beautiful channel concept Raja, and we're gonna today we'll cover that topic like a potential of a due to uniform solid sphere. So this we are talking about the gravitational potential here. Okay, and we have already discussed the to achieve to the the uniform solid sphere will come from the we start from the ring. Through the ring we created the a hollow sphere. Now integrating the hollow sphere, so we are keep using the mathematical technique integration, correct? This is very important, like we have to you keep using the integration for our for all this purpose. So this is the the integration technique we're going to use, and will now today we'll derive the formula for the potential due to uniform solid sphere. Now we already discussed it, okay, before that to create a uniform solid sphere, correct? How we can do that? Like uniform solid sphere, if you think that suppose this is a solid sphere, uniform solid sphere, this is a 3D picture. Imagine this is not a circle. Okay, we can come up with a small small uh, hollow sphere. Okay, we can keep integrating this infinity hollow sphere, correct, to achieve to the to get a heavy to get a solid sphere, correct? Or let's draw in some other way, like this is a solid sphere. Okay, with that center what I can do, I can draw one, I can cut, this is a small solid sphere. Okay, I can cut, and here we can cut another small with the some length, another sphere, and this in between, imagine this is a hollow sphere, correct? So like infinity hollow sphere we can draw from the concentric hollow sphere, correct? Like every will have the same center. Okay, and we can come up with a solid sphere. Okay, I think this is clear, correct? I think this is clear. Like with infinity concentric hollow spheres we're gonna integrate, and come with a solid sphere. And we have already calculated the or the potential due to a uniform thin hollow sphere or the thin shell, correct? This is the inside and this is outside. What we have come up in the formulas, we know, like so I write the formula here for the hollow sphere or thin thin shell. Okay, what is the formula we have come up with? That potential if r is greater than a. What is r and what is a? In the last video we have already discussed. R is the distance of the point from the center of the sphere, correct? And a is the radius of the sphere. So if it is outside, that means r greater than a, so the potential at any distance would be g m by r. Okay, this will be negative. And why it is negative we have already discussed. But potential, this is a this is the scalar quantity, not a vector quantity, correct? So it is not about direction, it is the value itself is a negative value. And why it is negative value we have already discussed. And inside means the situation when r is less than a, correct? Like sphere inside, if it is any falling inside, then the potential is g m by a, so that is constant. Okay, now we are seeing that potential will remain constant inside the sphere. Okay, this is all talking about the thin shell. And potential at outside, it is varying with the distance between the point and the center of the sphere. Now, and on the sphere also it will be like on the sphere, the if the the potential at the sphere on the surface of the sphere is g m by a, from the surface to the inside it is remain constant. Okay, good. Now what we gonna do here? Let's draw a, I'll try to draw one clean hollow sphere. Like I'll just insert a circle. Let's insert a circle. So just imagine this is a hollow sphere. Okay, so this is my hollow sphere. Okay, pretty good. Okay, now I am inserting, okay, I am creating from the center, same center, I am taking the same center, okay, and I am creating a hollow, sorry, this is, so the same center. Now, uh, I just, one of the sphere, I have, see, one of the sphere I have created here, this is a hollow sphere, okay, which, yeah, so same center. Now, so from this picture what we are seeing that this is the same center I have created. This is the sphere, just imagine this is a, I'm putting the sphere in a 2D frame, so it looks like that. And this is the, you know the this is the one of the hollow sphere I have taken. Okay, where I have taken this, I have taken it some distance. Okay, and let me, okay, okay, so I have taken it some distance. Okay, so this distance, the distance means the radius of this sphere I have taken it as x. Okay, and you can see there is a slight thickness I have taken. What is that? The thickness of this is dx. Why? Okay, so in physics already we have keep saying one thing, that d, whenever there is a dx means that there is a very small part actually I have taken here on this sphere. Okay, so what is the, now what is the, actually if I now, draw, calculate the, so this is hollow, this is the solid sphere. And solid sphere, what solid sphere, the mass is distributed, correct, for solid sphere. Now first we have to understand the mass distributed, okay, distributed all over the sphere, correct, not only on the surface, all over the sphere, correct. It is not only distributed on the surface area like what we have seen on the last, video, where for a hollow sphere or thin shell, mass is only distributed along the surface area, but here mass is distributed all over the sphere. Pretty good. Okay, now when it is all over the sphere, that means I have to calculate, suppose this is a sphere and mass is distributed everywhere, like inside also, correct. So now I have to calculate the volume of the sphere, correct. And what is the volume, and what is the, this is the radius, suppose this is the radius of the, uh, the, this is the x and this is the radius of the sphere is a, we are taking radius of the sphere is a. So what is the volume of the sphere? 4 by 3 pi a q is the volume of the solid sphere, correct, the whole sphere. Now as we have already discussed, okay, the, the radius of the sphere is a, and the distance, that I have taken a hollow sphere with x, you know from the radius of the hollow sphere is x, for example, and the thickness of the sphere is dx. So this is the hollow sphere. Now we know, okay, now we, so for the integration technique, like, for the last two videos I am using the integration. So through the integration technique, what we can say here is that we'll keep adding, like I told, correct, keep adding these hollow spheres and we'll get the, get the potential for the final sphere. So we'll calculate the, for each hollow sphere we'll calculate the potential using this formula, and finally we'll come up with the potential for the whole sphere. And potential is a scalar, so we can just simply we can add that values, correct, wherever the, for each hollow sphere we get the potential, we can keep adding the values. Okay, now this is the volume of the solid sphere, correct, volume of the solid sphere. What is that? Equal to 4 by 3 pi a q. Okay, now this is one of the hollow sphere I have taken x. Okay, in the integration, the mathematical, integration technique, what generally we do when we do integrate something, like integrate and come up with the final thing, like we parts by part we'll integrate, we'll take an arbitrary position some part, and then from that part we'll vary our limits, like integration limits from, from where to where we want to go, we can put that. So that's arbitrary, like I have taken a x distance. Now from the x distance I have taken a hollow sphere, okay, which thickness is dx. So what is the surface area of the hollow sphere? So we know the volume is nothing but the surface area into the height or thickness, correct? So on this formula, what is the surface area of the hollow sphere I have taken? 4 pi a square. Sorry, not a square. X is uh, the radius of the hollow sphere. Okay, and what is the height or thickness here is dx. So the volume of the hollow sphere I have taken. So this is the V of the thin shell I have taken, very thin shell, correct, dx. So this is the volume of the thing. So here so we have told we are calculating uniform solid sphere. That means the mass divided by volume. So here it is a we are talking about volumes, correct? So 3D scenario. So here we will use the the thing density, mass divided by volume. This is called density, and generally we represent it by rho, Greek letter rho. Okay, so the F is a uniform means the rho is similar wherever whatever the mass you take, you divide by volume, it will be rho. And this the thin, very thin. Okay, what should be the mass for this? We already we know, correct. This is dm, because we told know very small mass is dm. Okay, so now rho is same, like if I do mass divided by volume, rho is same always, correct. Rho of, if I take the whole sphere here rho, or if I take the small this part also, the rho always will be same. Okay, now what is the rho for the first? So this sphere with having a mass m and radius a. Okay, now as rho equal to same, rho equal to rho is same. So what we can do here is that what is the mass for this full sphere is that m divided by 4 by 3 pi a q, mass divided by volume, equal to this small sphere I have taken out here. So that will be dm divided by 4 pi x square dx. Okay, so why we are doing this, like why every time like we are checking, correct. Last video we have done it with the mass divided by area, here mass divided by volume. Why we are doing this? Because you can see here dm. Okay, each sphere, when you are keep adding the hollow spheres, okay, each sphere size is different. Based on the size, mass will be different, correct. So on that, so what we are doing here, we are representing dm with the function of a dx and x, correct, because we gonna vary the x, correct. Now when we calculate x from here to here, what to get the full sphere potential, what we can do, we'll vary the x from 0 to a, correct, to get the full sphere potential. So what is varying here? X is varying. Okay, now we represent dm as a function of x, so that when we apply the integration, that time it will be, when we vary the x, automatically dm will change, and we will achieve our integration, okay, to get the potential due to the sphere. That's the reason we are doing it. Now, so what we can do here from here, okay, so 4 pi a, so 4 pi will get cancelled, 4 pi will get cancelled. Okay, now what we are getting, dm equal to m, okay, 3m, correct, 3 will go up, m by 3m by aq into x square dx. Okay, so this is, okay, dm equal to 3m by aq x square dx. Okay, now from here we calculated the dm. Now what we will do to get a point, now we will calculate the potential at the point, okay, outside of the sphere and inside the sphere. Okay, now what is the dm we got on the last slide? Dm, dm equal to 3m by aq x square dx. So we have represent this one. And now let's, so what, so suppose this is the dm for a one hollow sphere, correct? Like one small hollow sphere, the dm is like that. Okay, so this is a one of the hollow sphere I have taken, okay, on the x distance, okay, from the center. So this is the dm mass. So for this dm, like if point is lying outside, like here p is here, okay, distance r from the center, like all these things we have already discussed on the last video when we calculate from the thin cell. Now dm is the mass, dm is the mass for the thin cell we have taken, okay, on the last slide, correct? Here it is the, this is the thin shell, correct? For it we will calculate the dm. Now, okay, now, so what should be the, now this is the dm, dm is the mass for the thin cell. Now based on the formula we know, if point is lying outside the, you know, outside the sphere, that means for this case r is greater than x, correct? If r is greater than x, point is like, or we can say x is less than r, both are same, correct? If this is the situation, then what should be the potential? dv, very small potential due to this dm mass, is nothing but the, we can write dm by r and minus. So dv will equal to minus 3m by aq, okay, sorry, gdm by r. Okay, then we can put the dm values here. Okay, now so this will be the, if it is inside, if it is outside, correct? Now if it is lying on the inside, like if r is less than x, or x is greater than r, for this situation what will happen? What is the dv? We know from the thin shell, so dv will be the minus g dm by x. X is the radius of the, the shell. Now x, it is on the r is less than x or less than equal to x or greater than equal to r. So this is the two situation. Now here g is now, so now the situation where r is like point is outside the sphere, correct? So what is the integration of dv is equal to v potential, okay, we have taken the integration, and g by r, and I can write dm, and integration of dm, correct? G is constant, r is constant, dm is changing, correct? And if I so minus, and if I keep integrating all the dm mass, what will happen? It will become gm by r, correct? So the gravitational potential, now this is the point is outside, point is outside. So if point is outside, then we are seeing here is that the gravitational potential, okay, due to a solid sphere is same as the hollow sphere, is same as the, you know, point mass, okay, as if that point mass, the hollow sphere, you know, whole mass is lying on the on the point, the center of the sphere. So this is the gravitational potential, it is same, correct? So we'll finally, when we finish this, we'll create a table where we can see that how the potential was, you know, varying due to different objects. So for point lying outside, no issues, correct? We have come up with this, and there is no issues. This is point lying outside. Same formula, correct? G m by r. Okay, where g is the gravitational constant, m is the mass of the sphere, total solid sphere, and r is the distance from the center to the point. Okay, now come to the second scenario. If point is inside the, you know, point lie inside the sphere, inside the sphere. So we are talking about here solid sphere. Now how it looks like, how it should be looks like, this is my, like this is my sphere. Okay, let me remove this. So this is my sphere. Now how the, so this is the center of the sphere. Now the point, suppose it is lying here, P is here. Okay, so this is our P. So here I am taking a sphere, again I am drawing a sphere here. This distance is R, correct? This distance is A. This is the radius of the, radius of the sphere. Now same thing like I did it for the, the hollow, like to calculate the, to make the solid sphere, we have, keep integrating the thin shell, correct? So here also we'll, at x distance, some arbitrary distance, what we do, we'll take a, we calculate a sphere. Okay, hollow sphere, we take a, we draw a hollow sphere, okay, with a some thickness, with some thickness is dx, and what is the distance from the, what is the radius, is that x. Now why we do that, like now point is inside the P. Okay, and for solid sphere, mass is all over the sphere, correct? It is not only the surface area, it is all over the sphere. And we already calculated the, the density, and we calculated the density equal, and we, get the dm and all that thing. And what is, so here same thing, like at the x distance we have, stripped out a small, thin hollow sphere whose mass is dm, okay, thickness is dx, okay, and radius is x, correct? And then we can come up with the same thing, correct? Like we can come up the dm equal to the same formula, 3m by aq x square dx. We can come up with the same formula. Okay, that is fine. Let's concentrate now. Now point is inside. Okay, up to this sphere, like up to this sphere with radius r, the point is looks like it is on the surface of the sphere. So what is the gravitational potential for the, you know so let's see, this is the gravitational potential for this, case. So for that I am taking, for example, I am just representing it Vr, okay, equal to, due to the radius r is nothing but the minus g. See here I cannot take the m is the whole sphere mass, correct? I don't know what is the mass of this sphere, correct? I don't know. This is also solid sphere, but I don't know what is the mass, so I am just taking mass as m dash divided by r. That is the formula, correct? Because this is on the surface for this sphere, that is on the surface. We don't know what is m dash, so we can come up with the m dash with the same formula, correct? M dash, so I can, if again rho is nothing but the m dash, is the m dash divided by 4 by 3 pi r cube equal to, I can write m by 4 by 3 pi a cube. We can write that, correct? Because this is a uniform solid sphere. Now from here we can represent m dash, correct? Because rho is equal to this for this. Now I can cancel this 4 by 3 pi r cube, 4 by 3, pi, and I am getting m dash equal to m into r cube by a cube, correct? So now Vr is nothing but the minus g m dash by r, correct? Because it is on the surface for the sphere. Okay. Now what is the m dash, is nothing but the g. I can write in m dash, I can write m by m into r q by r into a q. R and r q will get cancelled, so it will becoming minus g m r square by a q. Okay. Okay, now let's draw again the, this is the picture. I'll draw it again in that. Now what we have calculated, this is our solid sphere. This is the center of the sphere. Okay, and the point is lying inside the sphere. So through that point I draw a solid sphere. Okay, I cut the solid sphere. This is inside the point, which is distance r from the center O. Okay, then I have taken a very thin, okay, with the thickness of dx, okay, and the x distance. What we have done on the last, last here, whatever we have done it here, same thing we are doing it here. Now what so we have already calculated the potential at the this point P due to the inside solid sphere, correct, and we got it, correct. So this is the this is the on this is for the solid sphere, this is this solid sphere, this is on the surface. So what is the VR is nothing but the, we got it as a minus g m r square by aq. Okay, because for the solid sphere we have already calculated it here, correct, like we have already calculated the yeah, if r is greater than a. Okay, so we have calculated that. Okay, so we can say that if r greater than x equal to here, so it will gm by r, or if it is on the surface, then it is gm by x or gm by r, whatever. Okay, so uh, in this here, what we can say, like this is minus gm r square by aq. So this is the point due to this solid sphere inside this solid sphere. Now there is a, now from here whatever the sphere, whatever the mass, because mass is distributed along whole whole sphere, correct. So inside this mass, due to this mass, we have the potential. But what is about outside? So outside we'll do the same technique, okay, what we use to calculate the solid sphere potential. Okay, solid sphere potential. So we create a small hollow sphere, and then we'll go slowly integrate that. From where to where we integrate now, because up to here we got the potential. Now from here to here, correct, like from x, like it will be from x will be vary from r to a, correct, we'll vary the x from r to a. Okay, now as we have taken at x distance, okay, at x distance, dm is the mass and dx is the thickness of a hollow sphere. Okay, and then we calculated the volume or thing, and we have come up with the formula dm equal to, we know that, correct, dm equal to 3m by aq x square dx. We have already derived this, correct, 3m by aq x square dx. Now the interesting thing is, this is very important, correct, for this all this hollow sphere, this r will be the internal point, not the external point, correct, like for this all hollow sphere, r is the internal point. And for the internal point, what is the, what is the potential for this x distance, like I have a dv, correct, dv is nothing but the minus g dm by x, correct, that is the internal point. We know internal hollow sphere, for a hollow sphere internal, at the internal gravitational potential is constant, correct. Now for this particular hollow sphere you have taken at a x distance, the gravitational potential dv is small, because of small dm mass, the dv is minus g dm by x. Okay, now I have to integrate the potential due to the outer shell. For this point, this all shell whatever we are gonna take will be outer shell, correct. For the outer shell, this is the gravitational potential for one of the shell I have taken, correct, with the dm mass. Now what I have to do, I have to integrate it minus g integrate dm by x. Now here I am gonna use this because x is a variable, dm I cannot integrate with the dm with x, correct. I have to represent dm with the function of x. Okay, and x will vary from where, I told x will vary from r to a. from all these outer cells, starting from here, I have to calculate the gravitational potential inside that. Okay, and put for each outer cell x will vary, and x will vary from r. It will start from r, it will go about to a. Okay, now minus g. Now I'll put the values, dm values, r to a 3m by aq x square dx by x. Correct? Now we can write it as a minus. So I'll take all the constant out. So this, see, 3 is constant, m is constant, a is constant, correct? So 3gm aq. Now I'll vary r to a. This will become x dx. So this is nothing but I can write minus 3gm by aq x square by 2, integration of x is x square by 2, it is r to a, equal to minus 3gm to aq. Okay, so here I'll put the values like a square by 2 minus r square by 2. Sorry, 2aq I have already taken out, so here I can do a square minus r square. I can put that a square minus r square. Okay, so the final formula is for the, is that equal to minus gm by 2aq. Okay, final formula is 3gm, this one. Okay, 1 minute, let me, this is the, I'll represent it as a, VA. Why VA? VA is the, the outside, like I'm taking like a VA is the you know uh, all the solid sphere, okay, is appearing, the point P will be appearing to the inside point for them, correct, the mass from R to A, or and VR is the mass is appearing as a outside sphere, correct. So VR means I've taken this point, or we can represent it as a V1, represent to V2. Now what is the final total potential? What is the total potential? I have to calculate the total potential. Okay, total potential nothing but the V1 plus V2, because potential is a scalar quantity and we can simply add that. Okay, so now, so the main concept here we applied for this point. Okay, for this sphere it will be looks like out at a surface point is on the surface, we use the formula this. For other outer shell, like for the outer sphere it is looks like a inside point. So we taken a small shells, thin shells, and then we integrate it, and this is the integration we have, and we come up with this formula, correct, 3gm by 2aq a square minus r square. Now total potential is nothing but I have to sum, correct. So for this, that is nothing but the minus gm by gm r square by aq, okay, minus 3gm 2aq, correct, into a square minus r square. So here what I can do, I can take the minus common. Now g aq, see, here it is 2aq, correct. So I can write gm, I can take common, correct. Now what is and this one is, okay, so this is the formula we have come up now, the potential of v1 plus v2. Okay, let's create another slide and we will solve it there. So when I create a new slide, okay, now what is that v1 total potential? Total potential is nothing but the total potential, correct, it is nothing but the V1 plus V2. So what was V1? V1 is nothing but the minus Gm R square by AQ. And what is the potential at the V2? V2 is nothing but the potential for the all the shell, thin shell. The point will be appearing inside, correct? For that we calculated 3 Gm by 2 AQ A square minus R square. Now I have to solve it, correct? So I can do it like I can take minus, Gm by AQ, I can take a common. Now what will remain here? R square minus A square minus R square, correct? So this will be, if I take a minus common, it will become plus, divided by 2. Okay, so this is minus Gm by AQ. This will be 3 will be there, correct? Because 3 is there now. So this is become 2R square plus 3A square minus 3R square by 2. So now I can take minus Gm by 2AQ. Okay, so it will become 2R square minus 3R square, so 3A square minus R square. So this will be the potential, total potential of the solid sphere, total potential of the solid sphere if point is inside the sphere, where A is the here G is the gravitational constant, M is the mass, A is the radius of the sphere, and R is the distance from the point, correct? Solid sphere. If point is point inside, what do you mean point inside? Suppose this is a solid sphere and the point somewhere it is lying here, so this distance is R and this is A. So that is the formula for the, so for the solid sphere the different formula. For the hollow sphere you have seen this is like a minus Gm by A, but here the formula is Gm by 2AQ 3A square minus R square. So we have seen the the three things. So like let's take like a hollow sphere and solid sphere, correct? This is the two things we have seen: hollow sphere and the solid sphere, correct? So what are the difference thing we have seen? Like inside and outside of the point, correct? If point is inside that, then the point is outside, then formula is minus Gm by R. Here also minus Gm by R. Is this is point outside, point on the sphere. On the sphere is nothing but the minus Gm by R. R is A here, correct? R will be the radius of the sphere. Here also minus Gm by A. Now when it comes to inside, the potential is drastically changing. Here it will be minus Gm by A, but here it will be minus Gm by 2AQ 3A square minus R square. You can remember this, correct? Okay. So this is the total description. Okay, total decision. So I just wanted to conceptually make you understand how the potential getting calculated. This is may not be needed for your school syllabus, okay, but this is good to know things, like good to know things in the sense how through integration we are achieving to the calculation of the potential on the different points on the sphere. So why we calculated all the things? Because this potential we need for the solid sphere is earth is nothing but the solid sphere. So when we will calculate the gravitational potential of a earth, correct, that time we will calculate this like inside the point, like this is the potential. Now for example, when it is the center, like center, what will happen at earth center? What is the potential if I ask you? Then what you tell? It is nothing but the minus Gm by 2AQ into 3A square. Here R will be 0, correct? R is the distance from the center. So now it will be becoming minus Gm 3Gm by 2A. So this is the potential at the center of the earth. Thank you very much. Okay, we'll come up with the next video. Thanks.